Hi, in this tutorial, I'll explain how to evaluate 3D surface components. In the previous tutorial, we showed how to evaluate a 2D specimen. This project shows a 3D component measured with an Aramis 3D camera. Since we use a stereo camera system, you can also use the right camera images. Since surface components are the foundation on which we build all other inspections, let's first create a surface component. Since the software was able to create starting facets for our surface, let's now change the color of this surface for better visibility. As we did with our 2D project, we need to make sure that our facet size is optimized for the speckle pattern, which was based on our field of view and sensor size. Once we have the correct speckle size, each facet should be large enough to contain 3 to 5 speckles. We can now use the same surface selection tools to define our area of interest as we did with the 2D project. We now have a 3D surface component ready to be inspected. Similar to the 2D project, we could again use a 3-2-1 alignment to create a reasonable coordinate system. However, we can also import CAD data into GOM Correlate, which we can use for the alignment. The goal is to transform the surface component into the coordinate system of the CAD with a best fit alignment. CAD data can be imported by dragging and dropping the file into the software. Select Add to Part. The software automatically opens an Import CAD dialog box. Click OK to import the CAD. Before we create an alignment, make only the surface component visible in the 3D view by left-clicking on it in the Overview Explorer and dragging and dropping it into the 3D view. Go to the plus sign in the upper right corner and use a 3-point alignment to pre-align the surface component to the CAD. Open the PIP window and left-click and drag and drop the CAD from the Overview Explorer tree into the PIP to make it exclusively visible. Orient the CAD as close as possible to the surface component before creating the alignment. Holding down Control, left-click a point on the CAD data and the corresponding point on the surface component. Do this 2 more times and click OK. Close the PIP and make sure the CAD is visible in the 3D view. You can now create the best fit alignment by going back to the plus sign and select Local Best Fit. The best fit alignment requires you to select which area of the surface component you want to align to the CAD data. We will select all points for this alignment. This can be done by right-clicking on the surface component and using Select All Points of Element. The surface component is now aligned to the CAD data. Let's now create some inspections. We can use displacement inspections to analyze the surface behavior during our test in the X, Y, and Z directions. You can see the part is deforming according to the legend color. Let's also take a look at the displacement in the Y direction. This inspection shows us the component becomes wider while also being moved downwards. The deformation of the component causes strains in this material. We can determine the positions at which these strains occur and their magnitude. We can now use the major strain function to analyze this. This inspection shows us the area where high strains are forming due to the deformation of the component. For this analysis, I am computing values against the reference stage. The reference stage is set to be the first stage in your test by default. This is why all the values are 0 at this stage. We can change the reference stage of the project at any time by right-clicking on the timeline and clicking Manage Stages. Select the desired stage and click on Set as Reference Stage. All values will then be computed against this new stage. You can also change it back at any time. Let's take a closer look at the high strain area by using a section line. We previously used a section line in viewing direction, but we can also use a section line parallel to the coordinate axis or even a local plane. Go to Construct, Section, Single Section. Let's select the y-axis to be our reference plane and a position at which we want to create the section. We can change the position value in the dialog box with the mouse wheel or by inputting a value. We can also control and left click on a point of interest on the surface component. In order to finish the creation, we need to select all points of the surface component. We can now make the section exclusively visible and apply the major strain inspection on the section line only. We can change the visualization of the section line in the Properties tab under Display. This way we can see the results as a color plot with a legend, as well as a typical plot available in the Diagram tab. In addition, we can also use deviation labels and point inspections on this section line. We can always view this data in the 3D view and in the Diagram tab. The diagram values for this point show the alternating strains seen during this test. If you would like to focus on a specific section of the timeline, you can create something called a stage range. Select a section of the timeline or diagram with Shift and the left mouse button. Right-click on the timeline and choose Stage Ranges, Create Stage Range. You can give this stage range any name you desire to better identify it. If you double-click on the stage range in the timeline, it becomes exclusively visible in the timeline. To see the whole timeline, click the X at the end of the timeline. We can now create a report page with the content from the 3D view and the diagram. We can also make the report page based solely on the created stage range or on the whole timeline. The videos and diagrams on the report page will reflect which stage range is currently visible. Now it's your turn. Practice the steps in this tutorial by opening GOM Correlate and selecting the 3D project GOM Testing Object component located in the sample data icon. Next, create a surface component. Remember to choose the correct facet size for the speckle pattern. Also change the front side color for better visibility. You can find more information on surface components through the direct help. Now create a 3-point alignment using the CAD model that has already been imported into the project. Make sure that the CAD model is exclusively visible in the PIP window and that the surface component is exclusively visible in the 3D view. Finish up by using a local best fit alignment. With an appropriate alignment, you can now check the surface component for X and Y displacements and major strain. Practice changing the legend scaling to all visible stages. Also practice switching the reference stage and viewing the resulting changes. Create a single section at an area of interest and check that section for major strain. You could also create a deviation label on the resulting check. Remember that you have to create a check for the section line for your quantity of interest, even if you have already created that check on the surface component. Change the major strain check to display the legend colors. Next, create a stage range for one of the displacement cycles. And finally, create a 3D plus diagram style report page displaying only your created stage range. Export this report page as a video. If you feel comfortable with this exercise, feel free to start watching the next GOM Correlate tutorial, or for more information, visit Prealign.com. In the next tutorial, we'll create inspections on 3D point components.